Hi everyone and Assalamu alaikum. This is our chemical engineering thermodynamics group project. We are group 10 from section 2 with Dr. Noor Aisha Sayyidina Amin, and this is our group members. Firstly, Hamza Wa'il Muhammad and John Ki Fong, and lastly, me, Ali Muhammad Abdurrahim. I really hope you enjoy our presentation. Thank you. So, our goal in this project is to design a flash to separate the mixture between hexane and octane by using their difference of boiling points. Firstly, we need to review the process and the process typical conditions, like the overall composition, so operating temperature and the operating pressure. And we're gonna do all this while assuming that the mixture is an ideal solution. So our outcomes, we need to calculate the moles of vapor, moles of liquid, the liquid phase mole fraction, and the vapor phase mole fraction. So this is our overall diagram. H stands for hexane and O stands for octane. By using McMurray's organic chemistry 10th edition, we were able to get the boiling points of hexane and octane, so we can assume the perfect operation temperature and pressure. And our temperature is 80 degrees Celsius and our pressure is 60 kilopascals. So our basis is 100 moles fed per second, 0.5 mole of hexane per mole, and 0.5 mole of octane per mole. Our outcomes is two streams. The upper streams is in a vapor phase and the lower stream is in liquid phase. Thank you. So for solving this problem, we had some assumptions. First, the mixture is an ideal solution. The flash operator work with 100% efficiency. A steady state process, a basis of 100 mole fed mixture, for composition of 50% mole hexane and 50% mole octane.
Assalamu alaikum, my name is Hamza Wa'il. I will be covering the calculation part for the project. We're starting with the ln P equal to A minus B over T plus C. T is in degrees Celsius and the P represents the PSAT. This equation is found through the reference Richard M. Fiedler in 2005. The values of A, B, and C are found by another reference, Chemical Engineering Thermodynamic 8th edition. So once we found those values for hexane and octane, because those are the mixture in the fluid separation, so we plug in those values with the T is 80 degree as per the assumption inlet. So the P sat for hexane is 142.59 kPa, octane is 23.37 kPa. Now to find if the pressure inlet, the 60 kPa, is accurate or is plausible, we need to find the P bubble and the P due. So the P bubble is equal to x1 P1 plus x2 P2. This is found in the same reference book for the Richard M. Fiedler 2005, section 6.49. The x1 and x2 represents the composition for the element, and P1 and P2 represents the Psat for the respective elements. So x1 is 0.5 for hexane, x2 is 0.5 also for octane. So times it by each Psat, we get the P bubble equal to 82.98. The P due is equal to 1 over x1 over P1 plus x2 over P2. So we plug in the values, we get P due as 40.16 kPa. That means that the assumption pressure 60 kPa is less than 82.96, greater than 40.16, hence the calculation is possible and we can proceed as per the assumption. Now, to find the molar fraction of hexane and octane in both the liquid and gas phase, starting with the liquid, we just need to find one of the two and subtract it from 1, because the molar composition always adds up to 1. Now, starting with the hexane in the liquid phase x1 equal to P minus P2 sat over P1 sat minus P2 sat. This equation is found by Richard and Fiedler. For the hexane, P is the process pressure 60 kPa minus P2 sat, the octane P sat, which is 23.37 over P1 sat, the hexane one, 142.59 minus octane P sat, 23.37. Plug in these values in the calculator and we get 0.307 mole hexane per mole as the composition in the liquid phase. Subtracted from 1, because like I said, composition always adds up to 1, we get the octane composition in the liquid phase as 0.693 mole per mole. Going to the gas phase, YIP equal to XIP sat. The YI is the gas composition and the XI is the liquid composition. For hexane, Y1 is equal to 0.307, which we just found, the liquid composition for hexane, times its PSAT 142.59 over the process pressure is 60 kPa. And this equation is also found by Richard and Fiedler in section 6.42 as per shown in the image. So the composition of hexane in the gas phase is 0.7296 mole per mole. Do the same thing, subtract it from 1, we get it the octane one as 0.2704 mole per mole in the gas phase for octane. Finally, to find the number of moles in the vapor and liquid phase, we started with the overall balance, 100 equal to N1 plus N2. N1 represents the number of moles in the vapor phase, N2 is in the liquid phase. To find these two unknowns, we need to use another equation. It can either be octane balance or hexane balance, but we used hexane. The equation is input equal to output. The input, which is 0.5, the composition of hexane, times 100, which is the basis, is equal to 0.7296, the composition of hexane in the vapor phase, times N1, the number of moles of vapor, plus 0.307, composition of hexane in the liquid phase, times N2, the number of moles in the liquid phase. We use simultaneous equation between the hexane balance and overall balance to substitute N2 equal to 100 minus N1 to have only one unknown in one equation, which helps us to find N1, which becomes 45.67 moles, and this is the vapor phase. We substitute this number in the overall balance for to find the N2 equal to 100 minus 45.67, hence N2 is 54.33 moles in the liquid phase.
Hence, we will get the overall diagram which is shown as this slide. In a nutshell, we obtain the moles of vapor N1 equals to 45.67 mole and the moles of liquid N2 equals to 54.33 mole. For hexane, mole fraction of hexane Y1, which is in vapor state, is 0.7296 mole per mole, while in liquid state, X1 is 0.307 mole per mole. For octane, mole fraction of hexane Y2, which is in vapor state, is 0.2704 mole per mole, which while in liquid state, X2 is 0.693 mole per mole. It shows that more hexane is steam flow, while octane is more in the liquid form.
For our reference, the first reference we used to get the values of A, B, and C for the calculation. The second reference we used to get all the equations we need like Raoult's and Antoni. The third reference we used to get the boiling points of the hexane and octane. And for the last reference, we use it as a reference for the calculation and to get the values of the composition and temperature and pressure. Thank you for watching.
That is all. Thank you.